Here we go. Here is 4-4. So in this case, we're going to be talking about basically the probability of A and B, which is the probability that event A occurs in the first trial and event B occurs in the second trial. It is really important that we take into consideration that if the probability of A occurring affects the second event B. So we're going to call that a conditional probability. So B given A represents the probability of event B occurring after event A has already occurred. Reads as B given A. Basically what that means is that in the second event, that the first event had some type of implication in its probability. So for example, if I asked you guys the probability you fall or trip while you're walking down the street, you'd probably tell me, oh, it's very small. But if I said, what if the first event though was that your shoelace came untied, then what is the probability you trip? And a lot of you guys would say, oh, I guess it goes up a little bit more. You may not step on your shoelace, you might trip actually bending over, right? Or fall over doing that. So the formal multiplication rule is the probability of A and B is going to be equal to the probability of A times the probability of B given A. You can do simple algebra and you can move this probability over here if you want to have the probability of A. Or we can have, if we want to solve for the probability of B given A, the conditional probability, we can divide both sides by the probability of A. So just simple algebra, we can move things around if we need to, but it's a great formula. You should have this down in your notes. So here's the example I'm going to use. Two of the subjects in this table below about experiments with polygraph tests. The first person selected had a positive test result, and the second selected person had a negative test result. Okay, so remember what we said. We got to take into consideration that event A, the first event, has already occurred. So if we're thinking about this, that probably means that if we select one person and then we take one less out of there, that might mean there might be more. So intuitively, when finding the event A occurs in one trial and the event B occurs in the next, multiply the probability of event A by the probability of event B. But be sure that the probability of event B takes into account the previous occurrence of event A. So if we go to this one, the probability of the second negative given the first positive. Well, you can have basically the probability of first plus times the probability of second, negative. So this case right here is 57 out of 98, 57 being this row total here, out of the whole entire grand total, that's the positive, times, and this is where we basically took into consideration, we already selected one person out of there. So there's only 97 for us to select, and that's how we would calculate that out. A note of caution, always consider whether the events are independent or dependent. If they're independent, then that means that the probability of the first occurring does not impact the other. So the probability, for example, you trip and the probability the sky is blue. They seem independent, right? But let's say you're walking with somebody and you're holding their hand and they trip. And then your probability of tripping might be higher because you are somehow or other connected with them. And therefore the probabilities of you two are not dependent. So in general, probability that any sequence of events is simply the product of their corresponding probabilities when they are independent. You just multiply them across. Two events A and B are independent if the occurrence of one does not affect the probability of the occurrence of the other. Several events are similarly independent if the occurrence of any does not affect the probability of the occurrence of the others. If A and B are not independent, then they are said to be dependent. So here's an example for you. If you flip a coin and you flip a coin again, does it matter whether you had heads or tails on the first one? And we'll assume you have a fair coin, by the way, not like a double-headed coin or something or a weighted coin. The point being, it does not matter whether you got heads or tails on the first one because they're independent. So dependent events, two events are dependent if the occurrence of one of them affects the probability of the occurrence of the other. Does this not necessarily mean that one of the events is the cause of the other? So like, for example, my shoelace example is one where you might have causality, but does not necessarily mean that they cause one another. Treating dependent events as independent. So this is kind of a really neat thing to think about. We call it the cumbersome calculation rule. And basically, if you're going to take a small sample from a large population, In other words, it's rare to select the same item twice. A lot of times we can use the 5% guideline for cumbersome calculations. And the idea is that we can treat dependent events as independent. Pretty amazing. It allows us to do a lot of testing and assumptions about probabilities. You'll see here in a little bit. So suppose we have 50 drug test results are given from people who use drugs. So we have positive results and negative results. And they're all technically who use drugs. So we have a couple of false negatives, technically. If 2 of the 50 subjects are randomly selected with replacement means that you're putting them back into the pool. So that you still have the same total you're pulling from. Find the probability that the first person tested positive and the second person tested negative. So that would just be 44 divided by 50 times 6 divided by 50. And I'll show you that here on the next slide. Now, the bottom part says, repeat part A by assuming that the 2 subjects are selected without replacement. So without replacement means once you pull one out of the pool, there's one less person to take into consideration. So probability negative test result is 6/50ths. Yeah. Positive result is 44/50ths. We multiply those 2 together with replacement, meaning we put them back into the pool. We get basically 10.6% or 0.106. And without replacement, which means we pull one out and we don't put it back in, we see about 10.8% or 0.108. And you'll see that denominator is impacted by the one less person in the pool. Okay, here's one where the cumbersome calculation might be useful. Quality control and manufacturing assume that a batch of 100,000 heart pacemakers, including 99,950, are good and 50 that are defective. Hinting using our 5% rule, we're going to do this calculation. So 2 of those 100,000 pacemakers are randomly selected without replacement. Find the probability they are both good. Well, in that case, you just do 99,950 divided by 100,000 times 999,949 divided by 100,000. And that would be the probability both are good. But now you're going to see, like, if we do 20 of those 100 pacemakers, this could be a really big calculation. And so this is where the cumbersome calculation might be helpful. So in this case, this is what we're supposed to do, right? If you use the cumbersome calculation rule, you can just take this and square it. You'll see they are very close to each other in terms of their actual probabilities. Now, if we do it for 20, you have to do 20 individual calculations. It's not that big a deal, but it is rather cumbersome and maybe takes you a little bit longer time. If we treat them as independent, we can just multiply the independent probabilities 20 times over, right? So raise to the 20th power. We see that those probabilities are not very far off. So that's one of the things that's really helpful when we take a small sample from a big population. We can use that cumbersome calculation rule. Now, if you're going to use this, you would have to state that you're using it, and it has to be appropriate. 5% means you're not pulling more than 5% of the population when you're doing this. Okay, here's another example. When we have 2 different people are randomly selected from those in your class, I wish we were in class right now, right? Find the indicated probability by assuming that birthdays occur on the same day of the week with equal frequencies. So we have 2 scenarios. The probability that 2 people are born on the same day of the week, and then the probability that 2 people are both born on a Monday. Okay. These are different. They're asking 2 different things, right? So the first one is find the probability 2 people are born on the same day of the week. Does it matter what day the first person was born on? Think about it. Well, when we pick the second person, does it matter what day the first person was born on? Yes, because that's when we got to figure out whether they're on the same day or not. But basically, we have a 1 in 7 chance of getting it correct. Now, if 2 people are both born on Monday, they both have 1/7 and 1/7, and we multiply it. And so, in this case, because no particular day is specified, the first person can be born on any day, and then all you got to do is make sure the second person matches whatever the day the first person was born on. So that's how you got 1/7. And the second one, 2 people are both born on Monday. So we need to make sure the first person is born on a Monday. So we have a 1 in 7 chance there. And the second person born on a Monday is also 1/7. So probably they're both born on Monday is 1/7 times 1/7. So. Tree diagrams can be helpful in terms of visualizing how we can do probabilities. So, and you notice that it says if the number of possibilities is not too large. Yeah, if you end up with a really big tree diagram, it's not as helpful. But it can be visually nice to understand maybe the number of outcomes you might see. So in this case, we have a first question is true or false, and a second question that is a multiple choice of 5 different answers. Excuse me. And so you have 2 times 5, and you get 10 is the total number of combinations that we can have possible for solutions. So summary of the fundamental rules of the addition rule, we use OR. Multiplication rule, we use the AND. So so multiplication rule, the word and just a summary of these to make sure you guys get them clear. Here's another helpful diagram. It's in your text, but I love it because it's a flow chart. Apply the multiplication rule, right? So it's probably A and B, then it's multiplication rule. Are A and B independent? This is the first question you should ask. If they are independent, then you just do multiply the probability A times the probability B. If they're not, we have to have it conditional, right? So we have to have that probability of B has to be impacted by the event A, the first event occurring. So important applications of multiplication rule. How likely is it to get a string of either heads or tails? Each event is independent. I put the answers already on here so you can read them as I talk about them. Probability of 2 tails and 2 tosses, right, is 1/4, right? If you think about it, you could draw the sample space out. There'd be 4 possible events in there. You could have heads, 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 tails, tails, heads, and tails, tails. So there's only one way you can get 2 tails and 2 tosses. But there are 4 possible outcomes, so 1/4. How about no heads and 2 tosses? Well, the only way you can get no heads and 2 tosses is getting both tails. That's what my hint's saying, right? So how about this? We're going to make it a little trickier. The probability of at least 1 heads in 4 tosses. One of the ways you won't have at least 1 heads in 4 tosses. That'd be if you had all tails. But you want to have at least 1 head, right? So can you use the complement? Yes. Yes, you can. We're going to talk about this in 4.5 here in the next section, but just want to make sure you're aware of basically the at least 1 foreshadowing. So